Hi everyone, welcome to the first video, the first lecture if you may. No, I'm kidding. It's not a lecture, we're learning together. And today we have a heavy topic with derivatives. So starting out strong, and I'd like to help you understand them. So first, what are they? Who are they? Well, it's not a who, it's a mathematical topic of calculus. So the textbook definition is the rate of change of a function with respect to a variable. So, okay, so, you know, let me underline the important stuff. So, rate of change of a function with respect to a variable. So, that's the important stuff, but that still doesn't really help us understand what a derivative is. That's a little too scientific, in my humble opinion. So, let's talk about one thing I underlined, which is rate of change. So, here we have a function, y equals 2x. I hope it looks somewhat familiar. And let's talk about the rate of change. So the rate of change of y in terms of x, so y in terms of x, is just a fancy way of saying delta y over delta x. So the change of y in terms of the change of x. And this is equal to y1 minus y2 over x1 minus x2. This should start looking familiar. Uh, if you remember back to your Algebra 2 days, this is the equation for a slope. I believe that's Algebra 2. I can't remember on my days of Algebra 2, but that's the equation for a slope. That's the important thing. And okay, so what's the change of y in terms of the change of x for this given function, or the slope of it? It is 2. Okay, so we have rate of change down, which is the first important thing, and we have also respect to a variable. So y in terms of x gives us the rate of change in terms of the variable x. Okay, so boom boom, still a little bit confused on derivatives. So with calculus, we can find the instantaneous rate of change of a function over any point of said function, even if it's changing, unlike this line we have here. So let's boil that down. So the rate of change of this line here doesn't change at any point. It's always going to be 2. Oh, why did I write it 2? I don't know. But any point, the rate of change is 2. But what if the slope is changing? So I hope this function looks even more familiar. Well, not even more, but it's a parabola. And the rate of change of a parabola definitely changes. So this change right here, oh, this was not a good line. But this slope right here, you can draw a slope with the secant line. So a secant line is a line between 2 points on a function. So the slope definitely changes. Like, look at this slope and look at this slope. Definitely different. And I'm sorry, my secant lines don't look that good, but I hope you get the point. The slope is changing with this parabola. And, you know, um, yeah, so the slope is changing, sorry. And, but with calculus, we can find the instantaneous rate of change of this function. So that is the given rate of change, or the rate of change of a function at any given point. So I have a point labeled right here, and the rate of change would be equal to this line right here. This line is not a secant line, but it's a tangent line. So the definition of a tangent line is a line that intersects with one point on the function. And the slope of a tangent line is the derivative. So let's boil that down. So this slope, m, of this tangent line, m sub tan, equals the derivative of, whatever point that is. Okay, so that's all good and well, but let's let's dive more into derivatives. It's a really deep topic. But first, okay, let's talk about notation before we go into the formula of derivative, because you can't solve a derivative without a formula. I'm just helping you with the concept stuff. So, notation. Okay. So, famous mathematician Leibniz, his notation, he helped he's a founder of um, calculus along with Sir Isaac Newton, and he has his very own notation, and it's probably the supreme notation for derivatives, in my humble opinion. It's dy dx. And why I think it's so supreme? Well, look, delta y over delta x. It's similar. Change in y, change in y, change in x, change in x. Wow, those are circles, and they look kind of ugly. But that's why I like them. And it really, and the way to say this out loud so you can impress your math teacher is uh, the derivative of y. Okay, I'm not going to write this out. The derivative of y in terms of x is blah, blah, blah. And to find out that blah, 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 we'll go over the formula. Okay, so that's the first notation. Then we have prime notation, um, which is would be y prime. So this function right here, its name is y, and so the derivative would be y prime. It also is a function of x, so if you could guess the derivative, it would be f prime of x. Okay, so y prime is y prime and f prime of x. Okay, so those are the two derivatives. That's nice. Leibniz is better. I'm sure your teacher prefers Leibniz over prime, but that's what you have. Okay, so now let's go into the formula of derivatives. But before that, we should probably talk about limits. So you might have heard of limits in your pre-calculus days, but a limit essentially gives us, there we go. A limit is essentially the value of a function as it approaches some x value. Okay, so let's say we wanted the limit of this function y. So limit of y as x approaches, let's say 0. So as this value of y gets closer to 0, um, as the limit gets closer to 0, what is the y value? That's basically what this limit is asking us. So that's pretty easy. I should probably have labeled this. This is y equals x squared. So we can just plug that in. Y equals 0 squared for x, and that gives us 0. So the limit of y as x approaches 0 of x of the function y equals x squared is 0. Okay, that's limits in a nutshell. And this helps us determine, or this helps us derive the formula of derivative. So the formula of a derivative, it's long, but you'll get used to it hopefully. I mean, it's not that okay. Actually, no, I won't sugarcoat it. It's pretty long, and it's basically the limit of as h approaches 0, the limit of f of x plus h minus f of x all over h as h approaches 0. Okay, don't be worried. There's two variables, I know, but this is, not really a variable. It's kind of like a dummy variable, but that's besides the point. So you might look at this and be like, what the hell is this? Well, this, you can look at this more like, um, let's say like, it's more like the slope formula. So it's more like, you can look at it like this. It's derived from the slope formula because, as I said, a derivative is the slope of a tangent line. So this is how it looks like. And this, it might still look weird, but it's it's the slope formula. So f of x, we can write this as like y2, and f of x plus a delta x. So f of x, what this is, plus some delta x gives us y1. So that's y1 over minus y2 all over delta x. So delta x is x1 minus x2. So that is a slope, and these circles are ugly. And this is, the representation of, so this formula right here is a representation of this. Okay, so that's that. So looking at this formula, we have our, so this is the derivative of, this is the formula of a derivative. Okay, boom, boom, boom. That's good. Now let's try to use it. So let's say we wanted the derivative of y, and y equals 10x minus 5. So to find the instantaneous rate of change, I'm throwing the other definition of a derivative at you. That's a derivative. Instantaneous rate of change. Okay, it's f of x plus h minus f of x over h. Okay, so this is the formula. First, we would plug in um, our function. So y equals 10x minus 5 is the same as f of x. So y is a function of x. So that's why I'm writing it like this. So let's plug in x plus h into our x. So we get 10 times x plus h. So we just plugged in x plus h right here. Minus 5. So that's this part done. And then minus f of x, which is minus 10x minus 5. Make sure to do your parentheses. And then over h. Okay, so bada bing bada boom. Let's now write, let's now distribute our 10 and our negative 1 right here. So this is kind of like a negative 1. Simple, simple stuff. Okay, boom, boom, boom. Now we have that. Now we can do a little, not cancellation, but subtraction. Boom, boom. Okay, and then we could divide out this h, and we get the limit as h approaches 0 equals 10. So, okay, so our original equation was 10x minus 5. So dy dx equals 10. And that is correct. So that's a little bit about derivatives. I hope you could follow along. If you have any questions at all, please leave them in the comment section, and I'll be sure to answer them to the best of my ability. So thank you so much, and have a great day. Bye.